Let's do question number 24. Uh, HC Verma, volume 2, Gauss law. Now, this is a like very important concept that you should know. Like a lot of people are confused. Even I was confused. Not except that I'm in 10th standard, not in 12th. But anyways, this is charge Q and the total charge is Q and the total charge is minus 2Q. And we'll assume Q is greater than 0. It cannot, well, it is possible that it is less than 0, but for simplicities, we'll assume it Q is greater than 0. So it has a net positive charge, it has a net negative charge, and it's given neutral. They're saying find the charge appearing on the outer surface of the rightmost plate. Like of this plate, they're saying the find this charge. The charge, they're asking the charge, they're asking the charge that will appear on the right side of the rightmost plate. Yeah, outer surface of the rightmost plate. So how to do this? Look, before this, we need to have some kind of a conceptual clarity of how to add electrostatic fields of conductors. Like, let me give you an example. Let's not do it with conductors. It will seem confusing. Let's do it with charges instead. Let's say this is a point P. This is a charge plus Q, and this is a charge minus Q. Now it's very easy to add. This plus Q goes here, and this minus Q also goes here. Let's assume it's a positive charge. And so you have the net electric field Q's upon K cube upon R square times 2. Uh, on this side, if this side is taken as positive. Now, how did we get this? We actually had to make the vectors, and but every time we're not sure if this is negative or positive or not. If it was positive, then we have a net zero charge. Of course, I'm assuming they are equidistant from this point P. We have zero charge. So how did we get this? See, simply what we did was we took the electric field of this charge, kq by r square. We took the electric field, like, do not be confused with signs. Take the charge as it is. If it is negative, take negative. If it's positive, take positive. Like if it's minus q, take k minus q by r square. Do not get confused with signs. Now add another negative sign. If it was positive, we should have taken positive. It's negative, now take negative and add another positive sign in front of it. And then add it. It's negative, negative gets converts to positive, and so you have 2kq by r square if this side is taken as positive. And if it was positive, take as it is k plus q by r square, add a negative sign, and then add it to this one. So we have this cut is equal to 0, and we have 0 electric fields. But if the charges are on the same side, like if you have a plus q charge here and a plus q charge here, then you have to simply add. It's not you can, you have to simply add kq by r square. Do not add a negative sign, and then kq by r square, and then you get a net electric field here, 2kq by r square. And if it's negative, of course, I'm assuming they're at the same point almost. And if it's negative, so kq by r square, assuming it's positive, kq by r square positive here and minus kq by r square here, you directly add kq by r square minus q, and this has actually a deeper meaning. Why we get such values and why they say that attractive force We'll put a negative sign in front of attractive force. It has a deeper meaning, but we won't delve more into it. So, see, it is okay. Let's start with an assumption. It is neutral. So, it must have it some kind of charge must come on the surface because of these two charges. They're not same, right? And the opposite and the magnitude is also not. Some kind of charge must also come. Because that's negative. I'm just taking an assumption. Like if the charge is present on the surface, it it's just an assumption. It must be some kind of a positive charge. That's negative. Let's assume that. Let me assume the charge here is it's Q. It's just an assumption because it's what I said. It's neutral. So same amount of charge but negative must come on the other side. There is no second option. Either it's neutral or if a charge comes on one side, an opposite charge must come on the other side. They have actually. Let's talk about some universal truths. Universal truths about conductor is always, no matter what the outside conditions are, the outer surface or the surface must be equipotential and there must be zero electric field inside the conductor. It should be always true, no matter how bad the condition is. Okay, as plus q, so and it has minus q. Let me assume it has no this minus 2q has some charge. I do not know if it's positive or negative. Let me mark it as yellow. It's not visible. It's not yellow. It has some kind of a charge. Let me assume it's omega. Here, I'm not sure if it's positive or negative. Let me mark it as zero. I'm not sure if it's positive or negative. And this side, if the total charge is minus 2q, by simple algebra mathematics, the charge on this side must be with green, I'm saying, should be minus 2q minus omega. Only then if you add both of them, omega gets cut. And we have minus 2q as total charge. So this, what okay, say like, mm, mm, like what question mark? This is we do not know what charge is this. We do not know if these two charges are opposite to each other. If it's positive, it's negative. It can be that, of course, both cannot be positive. But it can be that both are negative, or one is negative, other is positive, or you know, vice versa. Now, what you take is you take a Gaussian surface. Take this as a Gaussian surface. Let me make the like little less opaque. So see, this is let me take it as a Gaussian surface. Now we know that, of course, the electric field they cannot be at an angle. Like by symmetric arguments, they cannot. They have to be horizontal. Anyways, but now the of course the electric field through this part must be zero. The flux only should be on these two close ends. Okay, wait a second. Uh, okay. So must be on these two sides. Now, if the net electric field is zero and the forces by these two, there is no force by these two charges. Why? If you take this surface, like if you take A as the area on both the sides, then the force by this is minus q upon 2 epsilon naught, and by this is q by, and they're on the same side. And if the point on the other side and the charge is on the same side, then you can directly add, right? That's what I said. Minus q upon 2 a epsilon naught, and it cuts. So you do not need to worry about them. On this side, of course, the electric field must be zero, and this side electric field must be zero. So as the electric field is zero, the charge inside upon epsilon naught must also be zero. So charge inside must be zero. This is plus q minus q is always is zero. Now, if the only charge present here is this omega that we assume, we don't know, then there must be, because the net charge is zero inside, the charge that is present here must be minus omega. And I do not know whether it's positive or negative or whatever. Let me assume it is a symbol, huh? It's at the rate. It's at the rate. And of course, the charge on the other side must be q plus omega, because then it has to be zero. Let me assume it is, it's orange. And what? It is wasting too much time actually on this. It has curly brackets. Okay. I just taken this. We do not know about this. But now what? Take a point here. Let's say it's point P, and it's side conductor, so the net electric field must be zero. The forces by these electric fields is already zero as I calculated. The only forces it's feeling it's because of this side and this side and this side and this side. It's the only way it's feeling the forces. Now, as I said, this is on one side and this are on the other side. So you have to take a negative and add. If you have adding, it does not matter with the sign of the charge. Just take this and take the negative of this and add the electric field. I'm not wrong. So the field by this is, if the surface area, let me assume of all is A on one side upon 2A, because the, see, it's sigma by 2 epsilon naught, right? So sigma becomes charge upon area, and hence and so on. So it's minus sign, then it's minus omega upon 2 epsilon naught is the same in all. It's of course zero, and this is, what is this? They are on the same side, so you can add them directly. Now, uh, this and this gets cut. Of course, this was oral. This, if this and this cuts, then this and this also gets cut. Or the opposite. So this and this gets cut. What we are left with is 2a epsilon naught. Negative of this is plus 2q plus omega upon 2 epsilon naught is equal to 0. Right, so of course 2 epsilon naught gets multiplied with the other side. It becomes 3 theta. I'm saying a theta. It's 3 charge or 3q is equal to, or minus 3q is equal to 2 omega, and minus 3q on that side. So finally found omega. Oh yeah, omega. Okay, omega is minus 3q by 2. They ask us for the charge on this side. So let's do it. It's minus 2q minus of minus omega, that's 3q by 2. So minus 2 plus 1.5. It's minus theta. Oh, theta, I'm saying it's minus q by 2. If you want to know the charge on this side, it's theta minus theta by 2. So it's also minus theta by 2. So such a result is always it's written and on page number 139 after solving the example 8. It's a special case of the following result. When charged conducting plates are placed parallel to each other, the outermost surfaces get equal charges and the facing surfaces get equal and opposing charges. Yeah. So this was this and this gets opposite. So this minus omega, this plus omega. This is so 3q by 2. This is minus 3q by 2. And so on. So they both outermost surfaces get equal charges. So this the outermost surfaces got an equal charges. Wow. So that's how we get the answer. And that's how you can get the answer of other questions. I think I can solve question number 23 by the same fact. What they've taken is they've taken two plates, X and Y, given this a charge, Q, and this is neutral. Okay. So let me assume, just for a sec, that this is positive, so it gets negative charge here. Let me not use the colors. And because it's neutral, same amount of positive charge must come here where Q is greater than 0. If we take a Gaussian surface, yeah, of course, the net charge inside must be what? As the electric field is 0, the charge inside must be 0. The charge inside is 0, that means this minus Q and this is plus Q. So this is Q minus Q. Now, we do not know, like, I've just assumed it's negative, so I can just assume it's positive because I've assumed this is negative, but not necessary that Q is greater than 0 or Q is greater than 0, just assumed for simplicity. Do not know if it's positive or negative. Let's add question marks. Let's add positive. Now, what to do? What they have asked is the surface charge density at the inner surface of the plate. Of which plate? Of the plate X. So they have asked the surface charge density. Now, how to calculate? As I did earlier, take this point as P. Of course, add the electric fields Q minus Q upon. There is a simpler way to do it. Okay. Q minus Q upon 2 epsilon naught minus because these charges on the other side and these charges on one side. But these charges can be added without any, of course, confusion of signs because they are the same side, but these were on the opposite side. So we have to add a negative sign. So this is the negative sign. We can add these because they are the same side without the confusion of signs, no matter what the signs are. Minus Q upon, of course, it's like cut each other off. Then we have again plus Q upon 2a epsilon. This cuts and minus Q. So it becomes Q minus 2Q. Of course, the net electric field is 0. So it's 0. Q is equal to 2Q or Q is equal to Q by 2. They've asked us the A is the surface area. They've asked us the surface charge density at the inner surface of latex. So the charge here is Q by 2. And so, of course, area is Q by 2a. It can be done by simpler cases by taking into consideration that this is neutral, so there is no net force on this one because it's minus because it's sigma by 2 epsilon naught and it's minus sigma by 2 epsilon naught or no what the signs are. So it has no net electric field. So of course the charges will be distributed symmetrically. Now, the second question is the electric field at a point to the left of the plate. Now, to the left means here, let's take it as a point A. This has no electric field. The only electric field is because of this. Now, we have calculated it's Q by 2, so it's Q by 2 on both sides. Now net force on this is not because of this, but only because of this. Sigma by 2 epsilon naught. Because they are the same side, we can directly add. So Q upon 2A, Q upon 2A. Oh, sorry. It's sigma by 2 epsilon naught. Huh? So this is sigma by 2. This is sigma. This is sigma Q by 2A by 2 epsilon naught plus sigma by epsilon. Of course, the half gets cut and this whole thing gets cut. So this is the net electric field. They've asked the electric field, right? So they've assumed it as positive. So it's towards left. They've answered towards left, and then they asked the electric field between the plates. Of course, between the plates, because of this, there's none. Because of these two, it's just the same. Just on but on that side, so it's q by two epsilon, or on this side towards right, they're taking a positive. And at a point between the plates, at a point to the right of plates, of course, it's the same. Yeah. Like, what? They're just extremists just want like making us it's like emphasizing that this neutral plate gives no net electric field if it's large enough, of course. That's what the repetitions here mean. A, B, C, B, C, D. A is different, but B, C, D is repetition. Okay. So done two questions, 23 and 24. Thank you.